talk about sort of another framework I'm now working on. This one is for natural hazards engineering. We know the natural hazards is not just earthquake and tsunami that this country has to deal with. So what NSF is doing is they're funding what's called the NERI, and I'm working on basically a NERI project. These NERI projects are basically, they're providing infrastructure for researchers to do research. We're not actually doing the research ourselves. We're actually providing the infrastructure for those researchers, such as yourselves, who actually do research. The SIM Center, with the facility that I work with, is actually that facility responsible for providing infrastructure for researchers to do research in computational simulation with regards to natural hazards. There's a strong leadership team that's headquartered here at UC Berkeley. And as you see from the slide, like here, it's basically a multi-institution effort. We've got earthquake engineers here on the left of the country, and the wind people out on the right. So what are the types of software that the SIM Center is going to provide? For NERI, NSF looked at basically funded a number of grand challenge reports. And these reports for the different hazards identified certain software that was needed by researchers and those in industry. What were the software components needed? And they identified basically 4 types of software that were needed. We needed to change software from being deterministic to provide measures of uncertainty in the response. We needed software for performance-based engineering and software that allow engineers to work with others to do resiliency determination. And also we needed stuff to educate students and future engineers on the natural hazards. So our goal, in addition to providing EOC at the SIM Center, is to provide a new software framework that will allow those types of applications to be developed. What we want to do is take existing applications, merge them somehow together, so that we create at the end a much bigger application. How we do this, these are the types of applications we're going to provide. But how we do this is basically like any framework. We define what are the interfaces between the applications. We come up with pre and post processors so that we can use existing applications. We provide example applications, in this case example workflow applications, that show people how to use our framework, and they can see how they can extend it for their own research. Finally, to get people to use these things, we're providing front-end applications, nice user interfaces that allow particularly industry users to actually use these applications. And finally, we're about data collection. We need to verify and validate the software we're putting together. So the SIM Center is also involved in a lot of data collection. So for the rest of my talk, I'm basically going to talk about the largest type of application that we can put together with our framework. This is basically the sort of workflow application number 1. It's being led by Professors Mayhem and Deerling. The goal is to we're using the earthquake simulation that David just presented, this magnitude Hayward fault 7.0 scenario. We're looking at the data inventory from the Bay Area. And we're also using this other application called Urban Sim, which allows city planners to see the effects of policy decisions on transportation and land use on how that region is going to change. So we can use that software to see what would happen if an earthquake was to happen today, or if an earthquake was to happen to the region in, say, 2040, given sort of the current way that the city is evolving. Or city planners could go in and make changes to their policy, and then we can see, we run that 2040 simulation again to see the effect of the policy things on the damage that will occur after an earthquake. So however, let me get to the end by saying that the software what we're doing is not available for the general community yet. But we're going to release it through our website sometime in July. So all the results you're going to see are preliminary. We're still working on validating them and coming up with other use just to make sure that other researchers can come in and make changes to the workflow. So this is the ground simulation. It's the same one that David was presenting earlier. Actually got all the ground motion records from Marty Rogers up at Lawrence Livermore National Lab. So I won't talk about the simulation. The building inventory, this is what we're getting from a program called UrbanSim, which is developed here at UC Berkeley by somebody in city planning. He's actually not an earthquake engineer. What this code, as I say, does is it allows city planners to see the effects of policy changes, whether it's land use or transportation, on the built environment. For example, this is sort of looking at how buildings change over time. And what UrbanSim is, and I'm going to sort of talk about, leave the agent-based modeling to Kenichi in the last presentation, but it's an agent-based model whereby we have artificial intelligent agents working in a computer program. They're running around doing stuff. There's agents for the housing, there's agents for the household, the workers, the transportation network. Everything's there. It's all based on a lot of data. We've data about, at the individual parcel level, about what the house is used for, or what the parcel is used for. The residents of how many residents are living in a house, their income. So it contains an awful lot of information. And we're also in this workflow making use of software developed by Professor Liu at Tsinghua University, which for a given building will provide us a single multi-degree of freedom nonlinear structural analysis model for that building. And we're going to now use that in this workflow. So this is basically the workflow. The idea for every single building in the Bay Area, we're going to take the ground motions that David provided, and we're going to do a number of things with those buildings and the ground motion. First of all, we're going to create our analysis model input file. Then we're going to create, what are the EDPs for that event that the damage and loss tool is going to need. We're going to run the simulation. Finally, given the results of the simulation, we're going to calculate the downtime and loss. We're going to correlate all that data back into our built environment database, and that database is then shipped back to UrbanSim, and we allow them to plot currently the results of that simulation. And this is basically the example output that's coming from the analysis. This is for the 2010 event. With UrbanSim, I say we can go down to the parcel level and start looking at the damaged buildings. But what's also nice about it, we can start looking, instead of what's happening to the buildings, what's happening to the population. UrbanSim can show us the displaced population based on the scenario event. And we can start then, also looking at the displaced population via and versus their income level. So there's lots of information in UrbanSim that, as a civil engineer, I wouldn't care about. But as city planners start looking at it, this is the type of things they're interested in. Now there's some other stuff under the covers that I'm just going to briefly mention as a plug to actually get some help getting this information. Basically using a lot of artificial intelligence, creating expert systems. We're also applications that use machine learning. Those machine learning applications, and this is the plug, we need data to work on. What we're trying to do is create good simulation models of given a building. So what we need to do is capture experimental data, and we also need to capture simulation models of that experimental data so that when we're done, our artificial intelligence or our machine learning algorithms will be able to provide the simulation models given the experimental data. And why is that important? Well, we're doing what we're called ensemble predictions. We need multiple different models, simulation models for the different buildings. And we can't ask engineers to provide 2 or 3 different simulation models for a given building. So we're going to have our machine learning algorithms provide these simulations or these input files. So while we were developing the framework, like we're always thinking about how would researchers such as yourselves actually come along and use the framework or extend it so that you can do your own research. Basically, we got the buildings using a real crude method. There are other things we can do with the buildings. We can use David's canonical buildings. We could, if we had a database, if somebody had a database of actual buildings, we could start going to that database and getting the buildings from that. For the events, we had just one scenario of the Hayward event. For SCEC uses 40,000 scenario events when they're updating their ground motions. We could do something similar. We could use GMP's equations. Basically, other ways to come up with our simulation models, different EDPs. There's lots of different things we could do. And the thing is, we want to put this inside of the probabilistic framework. We want that uncertainty estimation in the output included in this. So we're wrapping uncertainty quantification around this whole workflow. And of course, it's not just buildings, it's also lifelines. And we're just calculating show us the buildings that are down, but we have to extend this framework now for other lifelines. ET, who's actually part of the Sim Center project, is going to talk about lifelines and workflows in the next presentation. And we're also looking at different events. We have to look at wind events, hurricanes, tornadoes, and also coastal inundation due to hurricanes. So what are, there's other questions there. How do we extend sort of the earthquake PVE to do other hazards? What are the EDPs? What are the fragility and cost functions? And with that, I'm done.